Okay, so now we're ready to use some examples to illustrate how to check convexity for multivariate functions and how to use that to do the solution. So let's consider a nonlinear program where we have two variables and the function is the following: x1 squared plus x2 squared plus x1 times x2 minus 2x1 minus 4x2. So from the figure, you may see that, well, it pretty much looks like a convex function because it has an upward curvature for any dimension. Seems to be. But maybe our eye may lie to us, so we need to do some numerical check. We need to do some analysis. So we may first find its gradient is this one. And we may further do some derivatives to find Hessians. So it's this one. Okay? So you may want to double check by yourself to make sure that you know how to do the calculations. Okay? So we don't really need the gradient. It's just we need to have our Hessian, and before that we need to first find gradient. So for that Hessian matrix 2, 1, 1, 2, we now want to check, for example, its eigenvalues. Okay? So the way to do it is to say, oh, okay, AX equals lambda X. So if you put lambda X to the left-hand side, then you may multiply that by I so that you may combine the two terms together. So you somehow need to do that. Otherwise, a matrix and a constant, they cannot subtract each other. So once you do that, then this somehow tells us that if you want to find any non-negative x to make this happens, then one condition you need is to have a minus lambda I having the determinant being 0. So again, I'm doing fast because this is linear algebra. So if you want to get all the things clear, maybe you need to help yourself. So somehow we need to check the determinant of a minus lambda I. So a is here. A minus lambda I would be for the diagonal, you get subtracted lambda. And then 1, 1 is still there. So you do the derivative here. You're going to see that 2 minus lambda squared minus 1 should be this one. And this guy should be 0. So that means all your lambda can be either 1 or 3, and they are all positive. All right? So somehow that means for this particular matrix 2, 1, 1, 2, the eigenvalues are all positive. Or for leading principal minors, we may also do that, and it may be easier if we are doing things by ourselves. So in this case, the first submatrix is 2, and its determinant is 2. And also for the whole matrix is 2, 1, 1, 2. The determinant is 3. So in that case, they are all positive, okay, or non-negative. So it's again positive semi-definite. So our gradient, our Hessian is positive semi-definite. So this function is convex. So the program is a convex program. Our first order condition says that, okay, you need to have your gradient being 0. So after you solve this 2 by 2 system, you're going to see, okay, our optimal solution is 0, 2. So this is how the analysis help us prove or help us find an optimal solution. Okay, for this particular function, now we have a systematic way to find its optimal solution. Through the analysis, we now may show that 0, 2 is really global optimal. So if you just do this with gradient descent, or you get a solution, it is guaranteed to be local mean, but you have no way to make sure that it is really a global mean. Unless you may say this is a quadratic function, this is a convex function, unless you may say it is convex. Otherwise, it would be hard in general to show one point is global optimal. Okay, so that's one thing. Let's consider another example. So in this example, we have a somewhat different function. Now this function is no longer quadratic, so you have a third order term. we may find its Hessian as this one. So I'm not going to go through the process. Please do it by yourself. And then let's see whether the Hessian matrix is positive semi-definite. So let's say I want to do the leading principal minor things. So the first leading principal minor is 6x1. I need that to be non-negative. I also have the second leading principal minor to be 6x1, okay, minus 16. So that's the second determinant. So in that case, this guy should also be non-negative. So collectively, I would see, oh, okay, x1 should be non-negative for the first condition. And for the second one, it says x1 must be at least 8/3. So that means the function is convex if and only if our x1 is greater than or equal to 8/3, according to the analysis with positive semi-definite matrices. Okay, so if x1 and x2 gives you the whole feasible region, then for those regions where your x1 is greater than 8/3, you know the function is convex here. Alright, so that's how we do the analysis.